Hello everybody, welcome to today's presentation. Today we're going to be speaking about our milestone 2 of our demoing our project for PRJ381. And our project was basically over our anti-sleep glasses and having people not fall asleep while they're driving. So I would just like to first give credit to everybody who worked on the project, which is obviously Kele, Kemi, Ketsu, Kagiso, Joseph, Keke, Kai, and myself. Okay, now moving on to Kagiso, who is going to be speaking about the system architecture.
As you can see, our system architecture is designed as a portable, low-cost, AI-driven solution. The architecture is structured into 3 main layers. We have the hardware, the server, and the dashboard. In the hardware layer, the ESP32 microcontroller collects data from the 2 sensors, the MPU, which detects the head movement, and the IR sensor, which detects the eye blinks. The system is powered by a rechargeable battery, and it includes LEDs and a buzzer to provide local alerts directly to the driver. We have the server layer where the ESP32 sends this sensor data over the Wi-Fi to the back end. The server loads the trained machine learning models, processes the incoming data in real time, and classifies whether the driver is awake or drowsy. We have the dashboard layer, which is the driver's interface. It is built using HTML, Bootstrap, and Chart.js, and it communicates with the server through socket.io. The dashboard displays live sensor graphs and triggers both visual and audio warnings whenever drowsiness is detected. As you can see that the architecture ensures smooth communication between the physical device, the AI logic, as well as the driver-facing interface, which makes the system reliable and responsive. To better visualize these interactions, we used the UML diagrams. In this use case diagram, we highlight 3 actors. We have the driver, the glasses, and the dashboard. The driver wears the glasses detect drowsiness and send alerts, and the dashboard provides both visual and audio warnings. This shows the overall interaction between the human user, the hardware device, as well as the dashboard. Next, we have the sequence diagram. It illustrates the flow of events step by step. The driver puts on the glasses, which begin to collect the sensor data. The glasses send this data to the server, where the machine learning model processes it. If drowsiness is detected, the server communicates with the dashboard, and the dashboard delivers warnings back to the driver. Together, the system architecture and the UML diagrams demonstrate how the data flows through the system and how the driver is kept safe throughout the real-time alerts. Thank you.
Next, we've got the technology stack. These are some of the hardware and software components that we've used. For the hardware, we've got the ESP32 dev model, which is for microcontrolling wireless comms running the firmware in C++. And then we've got the MPU, which is the accelerometer plus the gyroscope, which is for collecting motion data. We've got the battery, which is a portable power supply. We've got the LEDs and resistors for alerting indicators, a buzzer module for audible alerts for drowsiness, a push button for user input or to reset the alert, turn the system on and off as well. And then we've got the IR and photodiode module, or the IR obstacle sensor, which is for eye blink detection. And then we've also got the firmware on the ESP32. The language used is the C++. The libraries on platform IO dependencies are as listed. We've also got the IEDs that we used with the platform IO, which is a Visual Studio Code extension used for firmware development, building and uploading to the ESP, and then serial monitor via the platform IO for debugging and for the CSV logging.
All right, so my name is Guy Setati, and I'll be taking you through the data logging and machine learning. So for the purpose of the data flow, our ESP32 basically streams the IMU sensor data over serial or Wi-Fi, and it stores our files as CSV in our directories. And then for the frameworks and tools that we used Python 3.10 and others since we used multiple laptops. And then we also made use of the Jupyter Notebook Anaconda for experimenting with data. For the libraries that we used pandas to handle the CSV logs. We used NumPy for numerical operations. We used the matplotlib and Seaborn for visualization. We also used the scikit-learn for machine learning model training and evaluation. We also used models, the logic regression and random forest classifier. And we also used standard scaler for normalization of our data, and also joblib to save trained models. We also have under the files that the machine learning file output files that we have the scalar.pkl, which basically is for pre-processing or standardization. We also have the nodrf.pkl, which is basically for our trained random forest models. And we also have nodlf, which is basically for the trade logistic regression model. And moving on, the Server API, which we developed using the Python language. And we also use the frameworks Flask and Flask Socket IO. So basically, the server API handles ESP32 data via Wi-Fi, and it runs machine learning interference on incoming data. And it also it serves predictions, and it streams live updates to the dashboard via WebSockets. The dependencies that we used using this API are the Flask Socket IO, Eventlet or Event, the joblib, and pandas. And moving on for our dashboard, we made use of HTML templates, and we have 3 pages under called index, chart, and sign in. The index is for landing page, the chart is for live visualization of node detection, sign in is optional for the login user interface. Then under our styling and CSS, we use Bootstrap. Under JavaScript, we use the main.js, which is basically our client-side logic. We used under socket.io client, we have our real-time updates from our Flask server. Then under chart.js, we have graphs for drowsiness statistics. Then we also have images. All right, so for under the development tool and our workflow, as Kemi said, we use the Visual Studio with the extension platform IO for our firmware development and deployment. So we also use the Jupyter Notebook inside the Anaconda environment for machine learning prototyping. Then for our version control, we use GitHub. And then for project management, we used Trello, Notion, and Sheets. Then we use the testing frameworks being the Python PyTest and Unitest for testing the Python documents called test server and test training. Then we manually debugged our hardware with Platform IO serial monitor inside Visual Studio.
So we'll go through the workflow summary for our system and explain how the components interact. We start with the ESP32 firmware, which is written in C++. The ESP reads data from the MPU sensor and then sends the readings either through USB via serial or over the Wi-Fi for wireless connection. The readings are logged into a CSV file. For example, the data is collected in a file called imu_log.csv. Next, we move on to the machine learning stage where we use Python and Jupyter Notebook and for training and testing different models. And once the models are finalized, we save them as .pkl files. The server, which is built in Flask and socket.io, save these models. The server also accepts the live data coming directly from the ESP32. Once the data comes in, the server runs inference on it and classifies whether the person is awake or drowsy. And then the results would be displayed on the dashboard in our website. The dashboard is built using Bootstrap, chart.js, and a socket.io client. Or sends the alerts and even the graphs noting patterns to track drowsiness over time.
And now moving on to the summary of our work. First, we'll start with the API integration. Now, the API is essentially just the final puzzle piece to our project that just connects everything together. So the glasses will send data every half a second, and the API will check for warnings if something looks wrong, and looks wrong in the sense of there's dramatic head movement or the eyes have been closed for an extended period of time. And then this alert will then instantly show on the dashboard, and when it pops up on the dashboard, it will then immediately send the alert through back to the ESP which is where we have a buzzer and some LED lights that will wake up the person. And now for the third slide for our API, this is where we have security, deployment, risk, and deliverables. So our system obviously needs to be very safe and reliable because it does send health critical signals. So each device has its own secure pass, like unique digital ID. All communication is encrypted, not necessary, but it is just a nice to have. And then we did put limits on it so nothing can overload the server. We deploy it in containers, so it's easy to set up anywhere. We watch the system with health checks and logs. This is done through a database that's created, so where all the logs are stored, and then risks like false alarms, poor network, or device clocks being out of sync are expected. So we built retries, checks, and conservative thresholds.
Hello everyone, I am Kekeleto Malek. I will be explaining the MPU and Wi-Fi initialization for wireless connection. Unfortunately for now, we have only achieved the cable connection because we were trying to test the capability first before we transfer to the wireless connection. And on the slide, we are setting up the ESP32 to work with both the MPU 6050 motion sensor and the IR sensor, while also preparing it for Wi-Fi communication. First, we include the libraries needed for the MPU and Wi-Fi, then we define the Wi-Fi name, password, and the server URL where the data will be sent. We also initialize the MPU 6050 so it can capture motion data like acceleration and gyroscope readings. At the same time, we assign pins for the IR sensor and the LED. We define a drowsiness threshold that will later help us decide whether the driver is showing signs of sleepiness for the CSV file initialization. And here we start collecting live sensor data. Inside the setup, we configure the IR sensor pin as input and the LED as output. And then we print a CSV header so that the headings are saved in a structured format. In the loop, the MPU collects acceleration and gyroscope data while the IR sensor measures eye activity. We compare the IR value against the threshold to check for the drowsiness, and if the drowsiness is detected, the LED is switched on, otherwise it stays off. And then finally, we log all this data, time, accelerometer, gyroscope, IR sensor, and drowsiness state into CSV format, which we can later use for training and test our machine learning model. And then next we have the loop that relays live data, which is all just a display in, if I were to explain in a short way, because we put it all in a loop and it displays all the readings that we have mentioned as the thing runs, and then also saves it into a JSON format, which is string surrounded by curly brackets, and uses a HTTP request to post using the Wi-Fi connection that we have instantiated in the beginning, if we were to use a wireless connection. Otherwise, then we would just send the data over by connecting the different files in terms of the ML models and also the websites in order to refer all representations to there. Well, all the data needed for those representations to there. And the IR sensor module being implemented into the component configuration, which is then, as you can see, just the MPU ESP32 red light with a 220 ohm resistor, and also the IR sensor module, as well as the white lights to show that the system is on or off. Thank you very much. Now, moving on, now we are by the MPU readings, which is the readings we got from the MPU as we connected it to the ESP32 and built, upload, and ran the code that we have in order for the display to happen that way, which shows the gyroscope readings and accelerometer readings.
So when we were working on the design of the 3D glasses, we went through a few prototypes before getting to this version. The first three didn't print well, so we had to make some changes to improve durability and fit. In this prototype, we made the frame a bit thicker, which gives us enough space to fit essential components like the ESP32, the MPU 6050 sensor, and the battery. And even though it's thicker, we kept it lightweight so it's still comfortable to wear for extended periods. So this design is much more cleaner and modern and is practical for real life use. There's still some improvements we'd like to make, but for now, this is the best version we have that meets the functional requirements for the project.
Explaining how the system works by tracking blinking head movement, AI, using AI to detect drowsiness and triggering alerts when needed. Scrolling down, we explain how to use the glasses and give some key features. Then we prompt the user to connect the glasses in the dashboard. On the dashboard, we see live monitoring in action. At the top is the connection status, and below we have the 4 key panels: blink rate, drowsiness level, head movement, and alert status. Then we've got a real-time chart showing the changes in drowsiness during the session, along with statistics like total alerts and average blink rate. Then we've got the device status and past sessions displayed at the bottom. And finally, we have the settings where the user can adjust the threshold and export reports.
Now for the improvements and next steps. We spoke about currently of what we've already done, and the improvements that need to be made is basically just smoothing out some of the things that we've discussed previously. A thing that I can talk about mainly is we came into a bit of a roadblock with the BMW. So we have reached a point where the scripts that we want to run in order to retrieve certain information from the car and do certain things in the dashboard, we seem to have hit a wall with a conflict between security of the BMW's security features. So we believe we hit a firewall from the BMW, which is preventing us from further scripting. So then we're going to be looking into alternative ways to do what we want with the BMW, like play audio through the speakers and so on through Bluetooth. And then in terms of future plans as well, or what still needs to be done, the main thing that still needs to be done is taking the inputs from the ESP32 that we are getting and transmitting, and then just representing that data in a nicer format to be read on the dashboard through the website, so that it's just easy to see what is being recorded and what all the information means.
All right, so now moving on to the teamwork and collaboration. The whole point of this is to kind of show all of our work and how we have been working together. Some of us working individually and some of us partnering with each other, trying to help out and solve problems together. We were all pretty much at the hangar most of the time, being able to work with the car and all the different scripts that we're running. And so, yeah. Now just ending it off with a thank you, especially to our mentors who has helped and guided us to our project and what parts we would need and all these different specifications. And then last but not least, I would like to say thank you for our lecturers, especially Simba and Hain, for assisting us on the sprints that we had, on what is our next goals, what we should try and go for. And yeah, so just thank you for listening to this presentation, and I hope you really enjoyed it. Bye.